Hello everyone. First of all, I'm really excited to be here at ngBParty and to see such a great group of JavaScript enthusiasts. It's super cool. All right, today I'll be talking about Appmixer and how we built a scalable Dataflow engine in Node.js. But first, let me introduce myself a little bit. My name is Durman, and I'm the CEO of Client.io. We are a Prague-based startup company that specializes in building visual tools. We are the authors of the Join.js and Rapid diagramming framework, where Join.js is the open source part and Rapid is the commercial extension. By the way, how many of you have heard about Join.js? All right, Kerry, did you see it? I think we should improve on the marketing channels thing. Right, so Join.js and Rapid is a diagramming framework, like I said. So if you guys are building a visual tool that involves a diagramming components, basically anything that displays and interacts with graphs and diagrams, so nodes connected with lines, make sure to check it out, because it can save you time and provide a good foundation for start. But today I'd like to talk about Appmixer, which is a new platform we've been working on. I'll start with an introduction to what Appmixer is. Then I'll describe the tech stack behind Appmixer, and I'll move on to the technical design and where did we get the inspiration for the implementation of Appmixer, and I'll finish it up with some examples. All right. So what is Appmixer? Appmixer is a visual tool to connect your cloud applications together, synchronize data between them, and in general create API mashups in an easy and intuitive way. So it's kind of a visual programming language for connecting APIs. We can split Appmixer in three parts. The first is the API orchestration engine that I'll be talking about mostly. Then we have the HTML5 drag and drop mixing tool. Here is a screenshot. We have a new design already, but that's kind of the old one. And the real-time logs. But before I start talking about Appmixer engine, I'd like to give an introduction to sorry. I'll start with the tech stack first. All right, the tech stack behind Appmixer is pretty much all the engine code is written in Node.js. We store data in Mongo, and the communication between all the entities in the system is handled by RabbitMQ. RabbitMQ is an open source message broker. It's written in Erlang, and it supports a variety of messaging protocols such as MQTT, Stomp, and AMQP. We're mainly interested in AMQP here. Elastic, we store all the logs in Elastic. Elastic is a search engine. It's kind of like a database, but specialized for search. Logstash is just a collector of logs, so it's related to Elastic. It just collects logs. In our case, it subscribes to a queue in Rabbit and collects all the data coming into that queue and sends it to Elastic. Kibana, it's just a fancy UI for browsing and searching logs or data in Elastic. Everything is Dockerized and managed by OpenShift, where OpenShift is a product from Red Hat for managing and deploying containers. Basically, it's a distribution of Kubernetes from Google, plus some DevOps tools to accelerate application development. On the front-end side, the UI is written in React, and the diagramming editor is implemented using Join.js and Rapid. Oops. Right. Okay, so but before I start talking about the Appmixer engine, I'd like to give an introduction to the Dataflow paradigm. Now, how many of you have heard about the Dataflow paradigm? 1, 2, 3. All right, it's all Client.io guys. Great. And not all of them even. So right, so the Dataflow paradigm is a method of implementing software that is different from the classical von Neumann method. Right? It has some interesting features. It's inherently parallel, highly asynchronous. Operations are executed when input arguments are available. Right? Compare it to the von Neumann architecture with a program counter. Programs are usually represented as directed graphs, and it's a good basis for visual programming languages. Also, it's kind of related, it's very related actually to the actor model and reactive programming. Now, here we have some examples. So the classical von Neumann method of implementing software versus Dataflow. Sometimes the von Neumann is called a control flow versus Dataflow. Right, so here we have an example. We're trying to calculate C, which is a product of A and B, and to get to that, we need to calculate A, which equals x plus y, and B is y divided by 10. On the right side, we have an equivalent program written in a Dataflow paradigm. Right? So, like I said, it's usually represented as a graph where nodes represent operations, and then we have the data coming in. Right? Then on the bottom left, we have the von Neumann architecture. It's a simplified diagram here, by the way, but basically we have the CPU, we have the shared memory for both data and code, and we have some input and outputs, where the CPU consists of the control unit and the arithmetic logic unit, and the control unit contains the program counter, and the program counter tells the CPU where to fetch the next instruction from, right? Right, so what's interesting about it is that in the von Neumann method, the CPU, or the computer, needs 3 time units to calculate C, right? So it first calculates A, then B, and then C, right? In the Dataflow, assuming we have at least 2 processing units that then execute in parallel, we can get to C in only 2 time units, right? So we do the addition and division at the same time in the first time unit, and the second time unit we do the multiplication on the sub-result, and we get to C. Now, the order of operations in the von Neumann method is defined by the order of machine code instructions produced by the compiler or the developer, right? While on the Dataflow paradigm, the order of execution is defined by an explicit dependency graph, right? So the graph really describes the data dependencies, right? And the operations, they activate or fire or execute when the data is available, right? Dataflow, of course, the von Neumann method that's used almost everywhere, but a Dataflow is also used on many places, the signal processing, but also in spreadsheets, for example, right? You have a spreadsheet, you have cells, tables, and then some cells might depend on others. We might have some formulas, and if you change one cell, automatically all the other dependent cells are updated, right? Right. So the von Neumann method is a nice, simple conceptual model, but it has some flaws. For example, if an operation takes too long to execute, the CPU has to wait, even though there might be other operations in the pipeline that could possibly execute at the same time, right? Right, and that brings us to the Appmixer engine, which is highly inspired by the Dataflow paradigm. So we took many of the ideas of the Dataflow paradigm and applied it to the world of APIs. So it's API-oriented. The nodes in the Dataflow program in the Appmixer engine, we call them components, and they're basically like lightweight microservices. The engine has a REST interface, and it has a command line client. So you basically run the engine in a daemon mode, and then you can interact with it through the command line client or through the HTTP API, right? So you can start flows, stop flows, you can send messages to components, you can inspect the logs, and more. Like I mentioned, the engine is really API-oriented, and so it provides many of the capabilities that are very common when you're dealing with APIs. So the first thing is authentication, right? So the engine supports OAuth 1, OAuth 2, and API keys, which is pretty much the standard. It has support for quotas and limits, polling, webhooks, data transformations, coordination, branching, syncing, managing lifecycle of the components, Error handling and recovery, that's important one, really important one. If you want to have your API clients or API integrations robust enough, you have to be able to recover from failures, right? And then some support for managing state and logging. Now, I'd like to describe the most important entity in the system, which is the component. The component, here's an example of a component. So each component has 0 or more input and output ports. So here, this component has one input port, one output port. And below we see an example of a flow, a complete flow that connects 3 services together. In this case, that's MailChimp, Clearbit, and Google Spreadsheet. So what it does is that anytime there is a new subscriber in your MailChimp campaign, that email address of the subscriber is passed through the Clearbit API, where Clearbit is an API that takes an email address and it tries to find as much information about the person as possible, right? So it finds what is the company the person works for, how many employees the company has, in what industry the company operates, right? Does the user have a blog and Twitter handles, LinkedIn handles, and all that, right? And then we take the resulting object and we store it in our spreadsheet. All right, so each component consists of input and output ports. It has a definition, which is a pure Node.js module. And it has a manifest file. Call it a component JSON file, which contains metadata about the component, such as the name, icon, description, a definition of the input and output ports, and all that. I'll get back to that later. But the definition of the component that actually implements the behavior of the component, right? And so the programmer provides certain methods that the engine understands. So, for example, the receive method is called by the engine at right time. So this receive method is called anytime there is a new message on the component input port and the component is ready to activate, fire. Then we have the send method for sending data to the component output ports, which is then propagated to all the connected components. And we have tick and webhook that relates to polling and webhooks, and some lifecycle methods that the component can react on. Right. And now I'd like to describe how a component looks like under the hood. As you can imagine, messaging is a very important part of the whole system. And that's exactly where RabbitMQ excels in. So we use RabbitMQ heavily for connecting everything together for communication. And in our case, RabbitMQ has a notion of queues and exchanges. A queue is a data structure that holds messages that are sent to it in the order they arrived. While exchanges are routing algorithms that receive messages and propagate or distribute them to all the connected queues. Right? So in our case, each input port of a component is modeled as a queue on Rabbit, and each output port is modeled as an exchange. Right? Then we have a system of addressing, so the coordinator of the flow kind of knows how to connect everything together. But now I'd like to describe what happens when a message arrives on the component input port. So what happens is that the message comes, and the first thing the component does, or the engine does, is that it passes the incoming messages through something we call an input pipeline. And the input pipeline has 2 stages. Well, actually, the goal of the input pipeline is to check whether a component is ready to activate. The input pipeline has 2 stages, where the first stage is a check for matching fire patterns. Now, fire patterns is a mini language that specifies the requirements for the activation of the component based on the presence of data on the component input ports, right? So, for example, you might have a component sum, right? That has 2 input ports, A and B, and the task of the sum component is to calculate the sum of those two numbers and propagate it to the output port, right? So maybe this component requires data to be present on both the input ports, right? So the fire pattern in this case would look like 1, 1, right? So if the message passes through the fire pattern matching algorithm, then it goes to the second stage, which check if there are available quotas. The quotas allow you to kind of throttle the frequency of activation of the component, right? So you might say, okay, this component is only able to fire or process messages one at a time, right? Or maybe the component can process 5 messages at a time, or the component can process only 5 messages per hour, right? And if the message passes through that also, or to the second stage, then we create a message bundle. And the message bundle contains the maximum number of messages in the message bundle is the number of input ports, right? And then the message bundle is taken and it's put to the input queue. And the input queue is the queue where the component actually consumes messages from, right? And then the component consumes the message, does some processing, maybe calls some API, does some data transformations, and then this operation either succeeds or it fails, right? If it succeeds, then the component acknowledges the message to the engine, and at that time the message is assumed to be processed, and you know the component either sends other messages, generates other messages to the output port, or it just does nothing. Or the processing might fail, right? So you call an API and there was a network error, or you know the API provider had some failures, and the processing of the message fails. At this point, the component sends to the engine a negative acknowledgement, right? What the engine does in this case is that it takes the message bundle and it puts it into the retry queue, which is, by the way, the input, retry, and control queues are like the internal component queues. So it puts it into the retry queue, and it sets with a TTL value, the time to live value, decremented by 1. So there is some default TTL value at the beginning, and then every time the message bundle goes through the retry queue, the TTL value is decremented until it reaches 0, and at that point all the messages in the message bundle are discarded and never processed again. We still do store them in the database, but it never goes automatically back, but there is a possibility to manually send the message back to the component. Right, and then there is the last internal queue, which is the control queue, and that's where the component receives lifecycle messages from the coordinator of the flow. So those are like start, stop, reload, and others. The coordinator exchange contains messages that the component sends as replies to the control lifecycle messages. So it says like, I'm started, I'm stopped, right? So those two are very related. And then we have the log exchange. It's just used for sending logs, and then it goes to Logstash and then to Elastic. Right. So here we have a bigger picture, by the way, where we have 3 components connected together. You can see that you can connect more than one component to an output port of a component. Sometimes components that don't have input ports, we call them source components, and components that do not have output ports are called sink components. Here's an example of a component. So in this particular case, we've got the component Google Calendar create event that has only one input port, and the task of this component is to create a new event in your Google Calendar, right, based on the data that arrived to it. Right, so it's an OJS module. Like I said, we have the receive method, very important one. So the programmer implements the receive method. The receive method takes context as the only argument, and the context object contains everything you need to be able to call the API. Right, so, for example, we've got a context properties that contains the configuration of the component. We've got context messages, that's the actual message bundle, where keys of this object point to input port names, right? And the content sub-property or nested object is the actual data that arrived on the input port, right? Then we build up the event, and we call the Google API to create the event, to create the actual event in the Google Calendar, right? And then this either fails or it succeeds. And when it succeeds, we just acknowledge the message. If it fails, then we send a negative acknowledgement, and then it goes back to retry queue and tries again, like I mentioned before. And the last piece here is the context auth object, and that's kind of nice because the context auth object contains all the credentials you need to be able to call the API, right? So we've got access tokens or API keys, or yeah, that's basically it, right? There might be other information, like client ID, client secret, and all that. But what's nice about it is that the programmer of the component does not have to deal with all the authentication stuff, right? So they don't have to deal with requesting access tokens, refreshing tokens, anything like that. Everything is handled for them by the engine, right? So the programmer of the component can safely assume that the context auth object contains everything they need to be able to call the API. Here's an example of a component manifest file, just quickly. It contains the metadata of the component, so the name, icon, description, specifies the input and output port, the auth and quotas, and all the properties of the component. What's nice about it is that the properties, the developer of the manifest file just specify all that these are my properties of my component, and the Appmixer UI then takes this component manifest file and it automatically generates interactive HTML forms with all the validations and stuff for them. Right. And the last piece here is the flow descriptor, which kind of pieces all the components within one flow together, and is nothing else than just an encoding of the Dataflow program as a directed graph in JSON, right? So here's an example. We've got two components, and I'm not going to. This is pretty straightforward. So the two components are listed there, and all their connection is also encoded there. But it's important to note that this flow descriptor is accessible through the public API of the engine. So anyone can actually embed the functionality of the API integration of Appmixer into their third-party applications. So you can start flows, stop flows, modify flows, send messages to flows, and all that. Right, and just maybe one slide as the HTML5 mixing tool. Here's an example of the new design. So that's where the user actually creates those flows. They fill their properties in the inspector on the right side, and there's all the services that we currently support. There's more. So it's a visual drag and drop tool. The property editors are automatically generated out of the manifest file, and it's based on React, and the diagramming part is a Join.js and Rapid. So what's next? Appmixer, we are going to open the public API soon for developers. And in the middle of this year, somewhere July, we'll be launching a marketplace for custom components. So anyone can contribute new components to the system for other users to use. We'll be super happy if you guys have any feedback, or if you'd be interested in helping us building new components, or if you have some interesting use cases for applications that could integrate Appmixer. And last but not least, we are hiring. So if you're interested in working on either on Appmixer or Join.js and Rapid, please drop me a line. Here's my contact info, and thank you very much.